All right, everyone. How are we doing today? Doing all right? It is Monday. So, want to start off by thanking everyone for their patience with me last week. I never felt terribly sick, but uh, just had a cough I couldn't keep under control, and didn't seem like it was a good idea to be lecturing with that going on. So, anyway, do feel a little bit better now. My voice sounds a little bit scratchy. It's because I had a cough all last week, so hopefully that'll clear up fairly soon. I don't know exactly what I sound like. There's there's always that, like, the voice that you have that sounds to you like it has way more reverb than normal, or at least when it's recorded. Um, since it's so much closer to me, I'm sensitive to the fact that there's still a little bit of scratchiness in my throat, in my voice. I don't know how much of that's coming through on the recording, but that's what's going on there. Okay, and then try not to breathe too heavy into the microphone. I know that's hard to do too, and the mask makes that tricky. Uh, there's a date. I can find it. I have an email. I don't know what day it is. Okay, it might be Wednesday, or it'll be like next week. Then I'll have to check to see when that's going on. Okay, so last time, and I want to make sure that this is working here because I had to copy some files onto the server. I was working from my home computer last time. Okay, it seems to be fine. All right. So, if you look over here in the open or the current directory or current folder window, you'll notice that I have 3 folders here. And in each of those folders, there is an @ symbol in the directory name. And then inside of those folders, we have the file name that we were working on last time, which is the hour complex. So I'll press the plus sign here to show this. The most important thing to note is that this is black in the name of the text file because it is currently a member of the path. If I do something like make a new folder and say fall 2021, and I drag all of those other files and put them into that folder, you'll notice that this thing is grayed out currently because it's not in the path. And if I expand all that folder, all of those other files are grayed out because they're not in the path. If I try to use any of those files, MATLAB won't know what they are. Okay? But MATLAB does know what this file is. And also these other ones here. Okay? The reason that this is set up this way is because typically, if you were going to the trouble of writing a class file, the set of files that you have to define the class, there's going to be multiples associated with an individual class because they just tend to be more sophisticated than the types of things that we normally interact with. And we want to be able to collect all of these things in one place. Okay? So, for instance, if I were to open this file up and take a look at it, okay, we don't have any individual files here that are super long compared to what we would need to do for other things. But if for some reason we needed to have a separate file, what we could do is say type this like this, Okay. It's whining because, oh no, I hate that this does this so much. Sorry, it's doing the silly. Once I select it, it copies it. Nonsense. Okay. All right. We're gonna save this. It's whining because of that issue. All right. Okay. Now, what's going on here? Get rid of all that stuff. Is that I may need to redefine this. Okay. So I make an hour complex object, and you'll notice that I have an M file here that is inside of this folder. Okay, and it's a function that's defined. And the whole point is that that M file is supposed to go with the hour complex class. Okay. It's our division algorithm. I just grabbed one of them. It didn't matter which one I grabbed other than the constructor, because the constructor has to be in here, but any of the other methods could theoretically have been their own M files. If I take Z and divide it by Z, it works. Okay. But if I move this file out of the way and try to use that method, it's not defined. Okay. So if you need to make a sophisticated class that has very long methods, you don't have to put those all in one giant sprawling class definition file. You can break those methods up into their own M files and then just put them in the folder and structure your directory this way to keep those things. And what you have to do in order to make sure that MATLAB knows what this thing looks like is make a list of all of your stuff that's in separate files, like so. Okay, so if I wanted to say move this one, was this the whatever, that's fine. I'll just paste and figure out what it is. Okay, it's the polar coordinates one. Okay, list as many of these as you want, just like this. Make sure that their output structure is set up appropriately. And we get our outputs. The advantages are organization, because if you look at this file, individually, each of these functions are short, but a lot of the times, if you were writing a class, you would have methods that had much longer, more complicated sets of instructions associated with them. And we haven't been writing programs that are long enough to really come afoul of this rule, but it is generally considered to be best practice that you don't want any particular function to span multiple screens. Okay, you'd like to be able to see all the logic in one go, or if you're writing one particular function to maybe have a couple of screens for the code, but you generally don't want it to go longer than that. So mostly organizational. The other idea behind this would be to push toward the direction of something called object-oriented programming, which is just a much more compartmentalized version of programming, where if you remember the flowcharts that we wrote a few weeks ago, the idea is that each bit of the code, each specific task, even if there's multiple instructions involved in that task, will be its own separate file. And each of those things individually are constructed in a way to where we have a very discrete bits of pieces. Each thing has one specific task that it accomplishes, and if any piece in the chain breaks, you go investigate the very small, tiny thing so that you can fix this thing where the problem is, and then not have to worry about where that fits into the broad structure of the code. Do you have a question? Mm-hmm. Okay. Let me come look. See if I can track down the issue here. Mm-hmm. Okay. The trouble that you have is you're not in the directory structure. So, for the benefits of you watching the video, one of your classmates showed me what they had done, and what they had set up for their program was they made the changes to the files as I had typed them up and have shown on screen a couple of times already, but they had these things sitting out here in a main directory, okay, as opposed to having it inside of this special directory that has the same name as the class file with the @ symbol in front of it. Okay, this special type of inheritance that we're doing only works if these things are collected together in this file. So that's the secret sauce to make this go. Yeah, so the way that this works is regular old directories like this one down here are just a folder, okay? And if I wanted to, I could right click and go to the option here that says add this to the path, and then it would turn all these things black, and I could call all these functions, by name and MATLAB would recognize them. Okay? Now, I'm not going to do that because that distracts from the purpose of what we're talking about right now. The @ symbol in the folder name is something that is specific to interacting with classes in MATLAB. Okay? The only reason that this works is because this name is the same name as the class file inside of that folder. Okay? They have to match in order for this to work this way. These things, these other M files, inherit working from the fact that they are named in this file, the class definition file. If these lines weren't here, those other things wouldn't work. Okay, because they're not being invoked by the class in terms of being in the path. And then just for organization's sake, there needn't be a blank line in between those things. Okay, so does this hierarchy thing seem to make sense? Okay, now, for our purposes right now, we're not going to be doing things that are complicated enough that require this. I just wanted to mention it now before we move on, because this is how I'm going to organize things going forward for the rest of our time together as we're talking about classes, because it is the way that it's done. Okay, whenever people write classes, they put them in the folders that have the @ name, the @ symbol in front of the names to organize the files. So when they do get more sophisticated, you've already set up to put those files where they go. Okay. Now, where we want to go next is talking about the thing that I had given the preview for before our break for the last few days. And that is the quaternion class. Okay. So a quaternion has this kind of structure. It has 4 inputs as opposed to the 2 that a complex number has. And it has several of these and it has 3 imaginary units, I, J, and K. So we go over here to where I can write for a second. Quaternion, we'll use P as our base value. Okay. They look like this. There is a number A, and then a number B, a number C, and a number D. Okay. All 4 of those are real numbers, just like they would be if we were talking about something that's complex valued. And the relationship for those other letters, those special letters, are that I squared, J squared, K squared, and IJK, all those products are equal to -1. Okay? And then there are also several other identities where they follow the right-hand rule, basically, right? if you imagine each of these as corresponding to, sorry, I shouldn't put the hats on them. Been teaching too much Calc 3. All right. We think about them as roughly corresponding to the X, Y, and Z directions in 3D space, and use the right hand rule, and then multiply them as we're taking a cross product. So we know that I cross J is K, right? In terms of the right hand rule. Okay. And so we also know that the cross product is anti-commutative. I am not thinking of them as vectors. I'm using it to explain the algebraic relationship between the products of I, J, and K. You get the same answer as if you were taking the cross product. Okay, so just to be more specific and say it fully for the video, these things aren't vectors, all right? I'm just using the cross product because it's the easiest way to remember it. It works the same way as the cross product. I know you're familiar with the cross product. Okay, but the products end up working the same. So I times J is equal to K. J times I is negative K. All right. And you can see, now that you understand how that works, why I times J times K is always equal to negative 1. I times J is K. K times K is K squared, which is negative 1. Okay, and if you take any, these products don't commute, notably, right? I can't switch these around because I introduce minus signs if I do that. But I could also take J times K, which is I, and then I get I squared, which is negative 1. Okay. So anyway, that means, of course, there are 6 little identities like this, right? Each pair. Okay. This is the basics of how this works. Okay. Now, with this understanding, we can use these things more or less like they're complex numbers with more complicated arithmetic, right? If we go through and I say that I want to take P plus Q, where P and Q are 2 of these things, you would add like terms, right? Okay, assuming I just index the ABCD with 1s and 2 for P and Q. And we get things going here. Okay. So the reason we mention all of this, of course, is because we want to be able to, like we did for the complex numbers, set this up and be able to write a class that does the operations on these things, right? If I have some quaternion named P and make up some other quaternion named Q, and we'll make this one simple. We'll just make it 2 and then have all of the parts with letters be zeros. If I add P plus Q, they get added term by term. or if I make up some other quaternion, they still get added term by term. Okay. Now, the way that this works shouldn't be really any surprise based on the fact that we talked through how this worked for the complex number version of this. Now, the quaternion stuff has a little bit more bells and whistles because I wanted it to work in cases where we had scalar values that got added together, but otherwise, it's all fine, okay? What we have here is we added the real and imaginary parts together by extracting the information from A and B here, right? And then called our constructor with those new values in order to return a new complex number that had the appropriate set of values. In this code, if we want to do addition, what we do is we check to see if I'm adding a real number or a float, however you want to think about it, to a quaternion or not. If I'm adding two quaternions, then I just add them together like they're complex numbers, or like they're in the same procedure as if they're complex numbers, just with more terms because it's quaternion. But I also want to be able to do something like this. Number 2 plus a quaternion. Okay. That's what this is asking. Is did I type that instead? Right? Just a number plus the thing, and then I turn the number into quaternion, and then I add them together. Is basically what happens. Okay? This is obviously the most straightforward version of it, where we just make a new quaternion with the sums of the values added together. Okay? Now, this right here works in this case, but wouldn't necessarily work in the case of the complex number code because I made the constructor more sophisticated here. Okay? So, we talked about var again, right? It allows us to have variable length input lists. And the idea behind these variable length input lists is I've made quaternions so that I can give a vector of values, or I can give one individual value or 4 individual values. Okay? So just to demonstrate the different cases there, this just makes a quaternion that has the real part equal to 2 and then everything else equal to 0. This allows me to assign specific values to each of the entries. And this allows me to pass a vector. Okay, so those are the 3 different cases. I wrote the constructor that way to give it a little bit more flexibility and so that it would be easier and more efficient to write some of the other subsequent functions. So we make that piece a little bit more complicated so that other things can be simpler later on. All right. Questions about that? Seems okay. Varigan, in general, by the way, is an extremely powerful tool when it comes to setting up classes so that you have control over how much information you have to give at the outset. Okay. Here, we're still talking about setting up something that's pretty simple, right? It's just how many numbers do we pass to the code? But we could have something very sophisticated like, say, a plot command where there are some required inputs like the x and y values that we want to plot, and then a bunch of optional arguments like what color do we want it to be, what line style do we want, what marker size do we want. We need ways to specify all those things. And what the constructor for the plot handle class will do is go through and parse all those inputs using some kind of structure like this, usually looking for keywords, and then do the different things based on what those keyword values are. That's fine. So the question was, what would be an example of a keyword? And so if we're talking about plot commands and using that as a example, what we do is these two arguments are required, okay? And then this argument's actually the hardest one to deal with because it can be either colors or line styles, right? But we have a list of a finite number of those things that we go through. And then we say if there's more than so many inputs, okay, if there's, say, 3 or more inputs, if nr again is greater than or equal to 3, we start looking for keywords. And the rest of the argument has to be constructed as keyword and then thing that fits into what that keyword is supposed to do. Keyword and then thing that's supposed to fit into what that keyword's supposed to do. And so basically you go through, you find, you make a switch statement, a switch case statement, and you do it based on keywords and then assign the parameters as appropriate based on the keyword designations. We might have an element that is something like that in the project that we do that's going to tie all this together. But that's something I probably won't be able to get into until next week. All right. Not sure I need this one anymore. Okay. Now, for the quaternion class, there's a lot of work to recreate here that is relatively in line with what we talked about for our the complex class. Okay. We want to set up subtraction, we want to set up multiplication, we want to set up these other things, right? Except everything is just a little bit more work because there are more parameters involved, right? For instance, if we want to talk about multiplication, I don't want to write all those subscripts, so I'm going to use Greek letters. Okay, if we want to multiply these two things together, we end up with this this sort of thing here, right? And in order to write all this out, what we would need to do Oops. Is lots of distributing, right? We use the distribution property, we reorganize all these products, we apply the identities for I and J and K in order to switch them around, whatever letters they're going to be. We might pick up some minus signs, and then eventually we will get down to the point to where we have some expression that looks like something plus something I plus something J plus something K, right? Sorry, I'm looking something up here. I did a Google search for the wrong thing. I was too smart. Why did this unscroll? Okay, anyway, sorry. Turns out on the Wikipedia page for quaternions, there's a lot of useful information, and they go ahead and show you what this product looks like after you do the distribution and combinations of like terms. Okay, so you get a bunch of term pairs. It breaks up into the real part and the IJK part, like I mentioned. All right, and what we want to do is we want to not have some complicated version of this formula that goes in. We just want to give the computer the easiest thing to compute as possible, right? So we force feed it this thing, which is known as the Hamilton product. And that in cute linear algebra format is what is typed up here. Okay. So the idea behind what's going on is these first two cases are I'm multiplying a scalar number times a quaternion. And so it's a lot easier to do. I just multiply each element by the scalar. Okay, this is what happens when I have two quaternions that I'm multiplying together. And what I do is I take advantage of the fact that the multiplication can be thought of as a dot product. Right? So, where did my mouse go? There. Lagging. Okay, so this first line right here, it's not selecting. Okay, the line below where I try to select stuff because it's just a picture, is the first quaternion times the second quaternion with coefficients of 1, -1, -1, and -1. Okay? If we look at this expression here, this turns the value vector into a row vector. Okay? And I'm multiplying it times this expression here, which is a column vector. So you get row times a column, so all the elements get added up. Okay? This is the second quaternion's value list. And then I multiply element-wise by 1, -1, -1, and -1. This gives me the correct arithmetic signs in that expression and the values 1 to or sorry, 1, 2, 3, and 4 corresponding to A, B, C, D for the stuff with the 2 subscript, right? If you look at the subsequent lines down here, you'll notice that I reorder the vectors here because the letters in the second, third, and fourth lines are not in the same order. You'll see the A, B, C, and D for the subscript 2 stuff is switched around. It doesn't go A, B, C, D. It's B, A, D, C in the second one. Okay, so that's why I'm reordering the vector. 2 is B, 1 is A, 4 is D, 3 is C. And then I also multiply by the appropriate coefficients in order to introduce the arithmetic sign required. Okay, this is very, very cute, okay, but it's the shortest way to type make that product, right, for each of those individual pieces. I compute all 4 of those values, and then I pass them as a vector to my constructor in order to create a new quaternion that is the product of the 2 quaternions I had to begin with. Yes? Okay, so let me write out what, sorry, minimizing things I don't need to minimize. Let me write out what's happening here. Okay, so one of the lines in the MATLAB code is this. All right, I don't actually think that's necessary, but okay. So it looks like this, right? Now, the idea here is that p-value I'm going to use regular letters instead of or I'm not going to use subscripts. I'm going to use English letters and Greek letters again just to make this easier to write out. So p-value looks like this. Technically, that'd be p-value transpose, okay? Because we want it to look, what we want to multiply together eventually is A, B, C, D times beta, alpha, delta, negative gamma. Oops. That's the answer that we get, right? So what happens is Q dot value looks like this before I do anything to it, right? What having these numbers here does is it reorganizes it. So that's the trick. And then I should have written it as a column, but I'm not going to fix that right now. Okay, and then of course it picks up the arithmetic signs from being multiplied element-wise by the other vector. Okay. Yeah, no, that's why the parentheses here are really important to show what's going on. But I don't want it to be specific because there's a lot going on here in order to make this one line. But otherwise, you end up in a situation where if you try to type this kind of thing in directly, you end up having to type p dot value of 1 times q dot value of 2 and put the correct sign in front of it. It's a nightmare. Okay, so that's the big tricky thing. Is this is an example of doing the work outside of writing the program. You look at the mathematics, you figure out, okay, there's a formula for this, there's a condensed way that I can make this expression. So I'm going to go through the trouble of doing that and then give the program up the thing that's relatively easy to do, even though there was some extra trickery involved in coming up with a really short condensed expression to set that up. Okay? But when you do something really tricky like that, you leave a comment to say, this is what this thing is. So someone else can look up a Hamilton product and go, oh, okay, that's why this nonsense is here, is because we're making this computation easier to do. All right. So these other functions, again, are much like what we had before. The minus function is easy because we already have one that does addition correctly. Or we can do it like it is here, where we just subtract the two vectors and then make a new quaternion with the difference of the vectors, because we take our difference term by term. And our other functions are simple enough to do. Division is relatively easy. We use conjugates like we do for the complex numbers, right? I showed you the formula where we can multiply the numerator and denominator both by the conjugate of the denominator, and then we have in the denominator just the norm of the old denominator and then the product of the divisor and the dividend in the numerator. Or sorry, the divisor and we have the product of the dividend and the conjugate of the divisor. Those vocabulary terms are hard to keep straight when you don't use them very often. And those are the only ones we use, right? We talk about dividend, divisor, and quotient, but we never talk about add-ins or subtract-ins or multiplicand or anything like that, which are the elements of sums, differences, and products. Okay. All right. But this other stuff works just fine. The conjugation method works exactly the way that you want. You negate all the stuff that has letters and you leave the real value alone. So the conjugate of A bi plus cj plus dk is A minus bi minus cj minus dk. And the norm of a complex number is just the square root of the sum of the components. Or the square root of the square of the sum of the components. Yeah. Yeah, the whole point of this was that we have something that is pretty similar to complex numbers. And so we go through the exercise of learning how to program up the complex numbers, and using that understanding, I can then go through and show you something that's got a couple more teaspoons of sugar in terms of complication, but is basically the same thing. Okay. Well, there's the thing that we want to do with this is more complicated than what we did with the complex numbers, but the principle is the same. Okay, in terms of getting all the basic pieces going. More or less. The reason, okay, so I will answer your question, but I want to answer it in a more holistic way, to explain why this is so similar to complex numbers. There's a motivating factor here. All right. And it'll set us up for next class, where we're going to be talking about the exercise that I want us to do using this stuff. Okay. So we asked the question, why quaternions? And also, why is my writing pad thing freaking out? You're probably not asking that question, but I am. Okay. So if you recall, our discussion about complex numbers, one of the things that we eventually built towards when we were working with complex numbers was taking this form here with our a plus bi and converting, or at least being able to extract the information about the polar coordinates form of the complex number, right? We referred to r as the modulus and theta as the argument. Okay. But the basic idea here is that the complex number a plus bi has an alternate form in terms of polar coordinates. And the polar coordinates are encoded very, very nicely in terms of complex exponentials. Okay. Now, the magic here is what happens if we start talking about combinations of things. Imagine that we have two complex numbers, r1 e to the I theta 1 and r2 e to the I theta 2. Okay? The second complex number is going to have some other value theta and some other radius, but also can be written in polar coordinates. If we examine these things, and I rotate here theta 1, and I have my radius r here, and I have my other complex number, that say looks like this. I can take these two things and, to the best of my ability, combine them. Okay? So the idea was that I rotated by by theta 1, and then I added to that rotation theta 2, or did it in the opposite order, however you want to interpret the picture. Okay? Arithmetically, this rotation is represented by a product. If I multiply the two rotations together, e to the I theta, I just get e to the I quantity theta 1 plus theta 2. And the radius that I end up with is just the product of the moduli. This makes it extremely easy to talk about rotations in complex space. Okay? So if we kick over to MATLAB for a second, and take a look at some pretty easy to imagine things. Okay, if I imagine one points along the positive x-axis, right? If I take 1 and I multiply it times 1i, I get a rotation in the positive orientation by pi over 2 radians, or 90 degrees, however you want to think about it, right? If I take 1 and I multiply it times this, I get a rotation of pi over 4 radians. Okay, and of course we always want to measure theta in radians for the purposes of this discussion. I can plot this. Okay, and we see from the origin, which is right here, we have rotated 45 degrees, or pi over 4 radians. Okay, now the idea is that if I multiply this by, say, I, that should be a rotation of pi over 2 radians, which will put me in quadrant 2, right? But at the same height. Okay, it's kind of hard to see, but it is right here, right? Now I'm not drawing all the circles and everything, but the idea is that this is all in terms of rotations. Okay? So if we multiply by some factor that looks like this, where the modulus is equal to 1, this is a rotation about the origin of angle phi. Yeah, I know. It's kind of weird. We don't spend a lot of time talking about complex numbers. So I realize that some of that's new. You're just unaccustomed to working with these things. But the reason we care in this context is because rotations are products in complex space. Okay? The issue with this is that this only works in 2D. Okay? But it is amazingly useful. Okay? If you're in an environment where you want to talk about two-dimensional vectors and you want to be able to handle rotations about the origin in a very easy to do the arithmetic for kind of way, even if you don't care about complex numbers, one of the things that you might just do is say, you know what, I'm going to write everything down like it's a complex number anyway, because addition and subtraction work basically the same way, right? And if I want to rotate stuff, I can just use complex exponentials and rotate it and spin it around, even though I'm talking about two-dimensional real vectors. The arithmetic is more convenient if I take advantage of this slightly more sophisticated version of thinking about how the arithmetic works. Okay, so it is not uncommon to complexify the problem, okay, in order to get this kind of usefulness out of. All right, the relationship between this and quaternions is someone asked the question, this is amazingly easy to do in 2D. Why can't we come up with some three-dimensional version of this to be able to talk about rotations in 3D space that have a very nice way to do with just arithmetic, instead of having to worry about multiplying by matrices, which is normally the way that you do rotations in 2D or 3D. As you end up having to, if you're doing rotations in 2D, you would have a vector that looks like this, and then you would need to multiply it by, I might be misremembering exactly where the minus signs and stuff go, but some matrix that looks something like that, okay? And then this rotates around angle theta. It's a lot easier just to say, you know what, we're not going to worry about this. Huh? I have the negatives in the wrong spot. Okay. I'd rather do this. Okay, this matrix might be wrong, but it looks something like that. Okay? But if I think about them as complex numbers, I can just write that. Okay? What we want to do is come up with, is there some way using quaternions this works in 3D? Now, 3D has more problems, because instead of there being some very obvious origin that you're always rotating around, in 3D, what you're going to want to do is define some axis and rotate about it. Okay, and you have some point that sits out here in space, and it's going to travel along the arc. given basically imagine it sitting on a sphere of the appropriate radius, its distance from the origin, and then having the axis go down like that, and you rotate that point. This, after a bit of discussion, is actually a pretty easy arithmetic computation in quaternions once we understand enough about how quaternions work. Okay, so this is the motivating factor behind doing the setup for the quaternion class, is to have a system that can do the arithmetic for setting up this computation. All right, sorry about that. It's about to lose it. Anyway, so this is where I wanted to get to mainly today, was to talk about the quaternion things, give us a little bit of time to acclimate, see how it's basically the same as the complex numbers, just with more pieces, so that we can set up and be able to give you all an exercise to work on next time after a bit of discussion to talk about how to do these rotations. Okay? It's not going to be, in terms of arithmetic sophistication, that much more complicated than some formula that looks like this. It's a little bit worse, but it's not that bad once you have something that, once you understand how things work. The two bits that we have to deal with are defining the axis of rotation and then understanding how to use theta in order to talk about how much of a rotation we're doing about that axis. Okay, a couple formulas, making we get things defined appropriately, and then using the formula for rotations in terms of quaternions. All right. So do we have any questions before we call it for this evening here? All right. Okay. I'm don't seem to have any questions here live. I'll give the people out on the internet another little bit to get their stuff typed up if they have something. Or if not, let me know that you're doing okay, and we'll come back and set up our exercise for this stuff next time. All right, I think we're okay. So if you do have something that you want to email me about, please email me. By the way, go ahead and switch over to emailing me if you need to get a hold of me at the first name dot last name email address that instructors tend to have. The one listed in the syllabus, there was some stuff they had to, I think they're transitioning out of those email addresses, so my @math account probably isn't going to be working anymore. I think it might forward, but I'm not sure. But first name dot last name at wichita.edu is safer. My name is Nathan. There's no Nathaniel business going on for me. It's just Nathan. All right. Take care, everybody. I'll see you next time.